This video is a continuation from part 1. So this is our part 2, where we're going to focus on doing confidence interval for the difference between two population means and a hypothesis test when the population variances are unknown. So we want to look at this situation where sigma, let's do that. So we want the situation where sigma 1 squared is equal to sigma 2 squared is equal to sigma squared, but unknown. So we're assuming that they're equal, but we don't know what they are, all right? And so in that case, we want to find a confidence interval, and we want to do a hypothesis test for the difference between the population means. If we're doing a confidence interval, then we use the following for our confidence interval: x bar 1 minus x bar 2 plus or minus, we're going to use t alpha over 2 degrees of freedom, and then we will have this for our standard error, sp squared 1 over n1 plus 1 over n2. And then just for the test statistic, it's just simply a matter of, this again, the sample statistic minus the population parameter over the standard error. What's the standard error again? We already know what it is. sp squared 1 over n1, 1 over n2. All right? So that's what we're going to use. So let's go back to the problem details. And with the problem details, you may recall we said that we let 1 be men and 2 be women. And just in case you are starting from this video, you should watch part 1 first. But just to remind you, essentially we are looking to test whether or not there's a difference between the mean expenditures of men and women for Valentine's Day. And we had the following information. It was 40 men in our sample and 230 women. We had sample means of, for men, 135.67. That was what they spent. For women, it was X bar 2, $68.64 was the sample mean. And then we will see that the sample standard deviation. So we're going to treat the standard deviations as if they're sample. In the first case, we treated them like they were population, but now they are samples. 35 and S2 is now 20. All right? So given that we have that, all we need to do is to go ahead and find a confidence interval, and we will repeat the hypothesis test that we did in step 1. Not step 1, but part 1, video part 1. So let's do the confidence interval. So a 99% confidence interval for mu1 minus mu2 would be, I already gave you the formula up here, so we need to find a couple of things. We need the t value, which is our critical value, and then we're going to need sp squared. So let's just kind of figure out what those are. For the critical value, our t critical would be t alpha over 2. We know that alpha is 0.01, alpha over 2 is 0.005, so it's 0.005. And the degrees of freedom is n1 plus n2 minus 2. So degrees of freedom, if I just put it on the side here, would be 40 plus 30 minus 2 is 68. So 68 degrees of freedom. If we look up the t-table, that turns out to be 2.65. All right? And I'm assuming everyone knows how to use a t-table at this point in time. And then now let us, we need sp squared. So it's always good to just kind of, on the side, calculate what sp squared is. And sp squared is given by, I give you a formula for that in the first part. But just to remind you, I'll put it here and then put the values. So it's n1 minus 1 times s1 squared plus n2 minus 1 times s2 squared over the degrees of freedom, n1 plus n2 minus 2. And that, in our case, turns out to be 40 minus 1, 39 times 35 squared, plus 30 minus 1, 29 times 20 squared over 68. And then that turns out to be, and I believe 873.16. 873.16. All right? 873.16. And so now with that information, we could go ahead and put in the details for our confidence interval. So writing that in, we would have 135.67 minus 68.64. So that's our point estimate, plus or minus 2.65, which is our critical value. And in here we would have SP squared, which is 873.16, 1 over 40, 1 over 30. Turns out that when we do all of our calculations, this part, the first part right here, is 7 point something. Let me just grab my notes here, just bear with me for a second. And we have, turns out that this piece right here is 7.136. You can compute that for yourself. So we would actually have 67.03 as our point estimate of the difference, plus 2.65 times 7.136, which gives us an interval as follows: 67.03 plus or minus, and our margin of error in this case would be, let's make sure I get it right, 18.91. Okay, 18.91, which means that the confidence interval for the difference between mu1 and mu2, when we add and subtract, we will get 48.12 to $85.94. So we are 99% confident that the difference between the mean expenditures for men and women is somewhere between $48.12 and $85.94. Okay, that's what we currently believe the difference to be. But we're 99% confident of that. That means that there's a 1% chance it's not in that interval. All right, but with a 99% level of confidence, we can safely say that we do have evidence that men spend more on Valentine's on average than women. So that's what you would put as your concluding statement. So we are 99% confident men spend on average somewhere between $48.12 and $85.94 more than women on Valentine's. Okay, so that's what the information is telling us, that men spend somewhere between $48 and $85 more. Because remember, that's a confidence interval for the difference. So that's not what they're spending, that's the difference between what they're spending. And because any value in that interval is positive, then we have evidence that men are spending more on average. All right, so that's a confidence interval problem. Let us actually move to the hypothesis testing question. Our hypotheses are the same. The thing that changes is really our test statistic, our decision rule, and then, but we will basically go through the same 5-step process. All right. So 1, hypotheses. We are going to keep the same alpha 0.01, and then we are going to test, is there a difference between the mean expenditures? So hypotheses, HO, HA, there is no difference between the means versus there is a difference between the means. No difference between the means, population means that is, versus there is a difference between the population means. If we write that in symbols, HO and HA, then we are saying if there's no difference, that mu1 minus mu2 would be 0. In other words, mu1 is equal to mu2. But if we say that there is a difference, then mu1 minus mu2 is not 0. It could be negative, it could be positive. All right? Step 2, test statistic. The test statistic is simply t is equal to x bar 1 minus x bar 2 minus mu1 minus mu2, right? So it's always the sampling error is on the top. Sampling error is the sample statistic minus population parameter divided by the standard error. And for this case, we have SP squared 1 over N1, 1 over N2. All right, so we already know that. Let us squish and come up with the decision rule. Step 3. So this is a two-tailed test based on HA, which means that we have rejection regions in both tails. I could do a little better than that, I think. Let's see. If not, I'm going to just leave it as it is. All right. So rejection in one tail, rejection in the other tail, which is alpha over 2. So that would be 0.005. In which case, we've already found out that this is for the degrees of freedom that we have. It's negative 2.65 and positive 2.65. So we will reject the null hypothesis if we're in these regions. Reject HO. So we could say that if our Z value or the absolute value of Z is greater than or equal to 2.65, that means even if it is negative, if its absolute value takes you beyond 2.65, then you're in the rejection region. Reject the null hypothesis. All right? Good. And that's the decision rule. So now we want the analysis. And let's just put our values together. Kind of like that yellow, so I'm going to stick with it. For the analysis. So our t value, which is our observed t, is the x bar 1 minus x bar 2, which we already know is 67.03, minus the value from HO, which we know is 0. And the standard error we found earlier was 7.136. So we don't need to repeat everything. We already have it, 136. That actually gives us a value of 9.39. So that's our t-value. And of course, you can see that it's greater than 2.65. Let's find the p-value. P-value, all right, is, because a two-tailed test, twice the probability of t being greater than or equal to 9.39. We don't have that 9.39 in the t-table. If you go along the 68 degrees of freedom, if you go along that and you're trying to find 9.39, you won't find it. But what you will notice is that the smallest value in the table is 0.005. So which means that we know that this piece right here, this piece is less than 0.005. So since it is less than 0.005, if we multiply that by 2, we will get less than 0.01, right? So we could basically safely say that this is less than twice 0.005, which is less than 0.01. And that is less than alpha. So therefore, of course, we would reject the null hypothesis. But of course, given that t is 9.39, sin is less than 0.01 is not really indicating how dramatic it is. I'm sure it is a lot less than 0.01. But that's all our table allows us to say, given that we cannot go beyond, I think, the 2.65, right? Okay, so having said that, let us draw our conclusion. Step 5, decision, conclusion. So we'll say since 9.39 is much greater than 2.65, we will reject the null hypothesis. What do we conclude? Conclude we have strong evidence. Evidence that the means differ. Evidence that the population means differ. All right? Definitely strong evidence. So if we reject the null hypothesis, the risk is the risk of type 1 error, risk of type 1 error, and the probability of type 1 error, p type 1 error, is just our p-value, which is less than 0.01. All right, and then that brings us to the end of a hypothesis test where the population variances are not known. We make the assumption that they are the same. Now, in our textbook, if you follow the textbook and you have a copy of it, you will notice that the textbook actually deals with it differently. But we're not going to use that approach because the calculation of the degrees of freedom is a bit messy. All right, so your textbook, basically, if you follow their approach, what happens is that they don't assume those variances are the same. They assume that they're actually not the same, which means a more reasonable assumption. And therefore, they would use t is equal to x bar 1 minus x bar 2, mu1 minus mu2. They use that instead. And then they just go ahead and use the sample estimates that you have. S2 squared over M2, which would make life a whole lot easier. We wouldn't have to find SP squared. But then the degrees of freedom formula, wow. There's some kind of, I don't know if you look in the book, I just can't remember it. It has some, with calculations. Something over this, over something here, over something here. We don't need to do that, all of that work, so we will just essentially ignore this assumption and assume that the population variances are the same and use the approach that I just showed you earlier. Okay, so that is the end of part 2 of our video. I'm now going to go to part 3, and part 3 will focus on matched pairs. See you in the next video.